Recording in progress.
Hello. Is done?
Recording stopped.
Okay. Correct. Start. Okay. Okay. So, how many of you have looked at the question papers, the 10 questions which I wrote? Just looked at. I'm not asking that you solve. You looked at. Oh, okay. So some, yeah, okay. So and yeah, this is one of the questions, right? I mean, which I say that if you have, yeah. So all I wanted to do yesterday is just rehearse a little bit about, matrix multiplications and whatever, and how to calculate product of matrices, trace of matrices, particularly some of in the thermodynamic or L, some t to the power n. Okay, so this is what I was doing. But for summary, let me tell you these are the equations which I'll use. Let me explain each of them again. Okay, because this class, particularly this class, is something about a technique, right? I mean, I will discuss about a technique. So I cannot escape doing calculations, right? I mean, otherwise, what's the technique? I mean, so I have to tell you, like I will give you the ideas, but at the same time, some problem I have to do exactly. So for that, you need to know, like matrix multiplication, diagonalization of matrices, nothing more, nothing less. Okay, so I was repeating those. There is nothing hidden there. So let us repeat this again. Okay, so for every matrix T, good matrix, I will not define what is good. All matrices which I use in the class are good. So now, I mean, that is all, because more than that, it will take again some time. So T, right? So every matrix T, there are, these are called eigenvalues. There are left eigenvectors and right eigenvectors. Okay. So what it happens that for every d by d dimensional square matrix, there are d eigenvalues, lambda k. For every eigenvalue, there is a right eigenvector, there is a left eigenvector. So you write T uk equal to lambda k uk. Okay. So the same statement can also be written as T. So if you write it like you have a matrix T, and if you lambda 1, so this is, let us say, U1, U2, U3, like that. If you call this as a matrix, this is a matrix because U1 is a column vector. If you write all of them together, you call it a matrix U. Okay? And if you multiply with a diagonal matrix basically lambda 1, U1, U1, like that, right? I mean, that is the diagonal matrix. So this 1, 1 appears here. So if you call this is U, the same equation tells you that this is T times U equal to U times D. Just check it yourself. T times U equal to U times D. Okay? U contains the right eigenvectors written one by one after other. Okay? So if you call that is U, this equation is same as TU equal to UD. What is this equation? This equation, like, because it's written on the left, so this will be V times T equal to D times V. Because this V, what is V matrix? V is, let us say, like V1, which is a row, V2, and like that. So this is also a square matrix. Okay? So there are D of them, each of them is thing, so this is DV. So this equation is TV equal to DV. So what happens is that if you have a symmetric matrix, then, I mean, you can take a transpose of this, then this will be T transpose, U transpose equal to D transpose, U transpose, and T transpose equal to T, if it is symmetric. Then what will happen, that V transpose is same as U transpose is V. Okay? So all through quantum mechanics and many other problems in physics, you deal with either Hermitian operator, okay, which is the complex version of symmetric matrix. Because if you take a Hermitian and if you demand that it has to be real, you will get symmetric. Symmetric means transpose equal to this. So in quantum mechanics, like, what you write is like this vector. If you dagger, it becomes this vector. Because T, in general, what I'm doing here, will be non-Hermitian or non-symmetric. It will be real and it may not be symmetric. Okay? So in that case, you have to bother about what are right eigenvectors, left eigenvectors. Okay? If the matrix is diagonalizable, then the left eigenvector, you can always do it a inverse there. So for example, so Tu equal to this, if you make a universe, and if you say that U inverse exists, then it will be, no, not like that. Don't do this. So you multiply U inverse. So if you multiply U inverse from left, then U inverse from here, and U inverse from right, then this will be T U inverse equal to D U inverse. This is identity. So this is Vt equal to dV. So this is U inverse and the rows. So the left eigenvectors are the rows of U inverse if it exists. Otherwise, you can still calculate it. Okay? So how to calculate the right eigenvector? You know. How to calculate the left eigenvector? Left eigenvectors are eigenvectors of T transpose. So this is what we want to do. This is first thing. Second thing, this is gone. I will not, okay. So now, every matrix T has a decomposition. So you have a double sum, Tij is a scalar, these are matrix element, Ij, summation over Ij, right? So basically a matrix like this can be written as 1, 1 plus this element plus 2, 1, 2 times this element, like that. The same matrix has a spectral decomposition in terms of this, lambda k, Vk and Uk. Unless otherwise specified, these are normalized because, right, I mean you can always normalize a vector, and if, I mean, and you know that if this is eigenvector, you know, any constant multiplication is also eigenvector. So the same one, which is a double sum, can also be written like that. Okay? Then what you have, once you have this, so the function of T will be just function of lambda. So any function, if you want to use f of T, then this will be f of lambda. This is being used in your quantum mechanics class, previous class, right? I mean, this has been used. Okay, so f of this. So particularly T to the power n is lambda k to the power n, this summation over k. And if you take n goes to infinity, if the largest eigenvalue is non-degenerate, which is in this case, because it's a finite, if it is a finite dimensional matrix, then this is non-degenerate, then it will be largest eigenvalue to the power thing, and this is the only vector which remains, because all of the other ones are 0. Do you agree with this statement? So T, as I say, T to the power n, this is equal to lambda 1 to the power n V1 U1, V1 U1, plus lambda 2 to the power n V2 U2, like that. So if you take this n is infinity, so you can take lambda 1, let us say lambda 1 is the maximum. So lambda 1 to the power n you can take common. So this is V1 U1 plus lambda 2 by lambda 1 whole to the power n, like that. But lambda 2 is certainly magnitude wise smaller than, at least the real part smaller than this value. So then this will be to the power n, so this will be all 0, that is the only thing which survives. So limit n goes to infinity, you can just drop everything. It is just the largest eigenvector, like this. Outer product of left and right eigenvectors times lambda max to the power n. Okay, so this is the one which I will be using repeatedly. I hope you know. In case some of you forgotten, I'm just writing it here. Okay. So in terms of matrices, that's all I use. I'll erase this now. And now next one I want to do is that this is also the master equation I write, m dp by dt equal to mp, okay? And I asked you to do calculation there, we'll do this. Determinant of m equal to 0, m eigenvectors of m is, right eigenvector is ek, lambda k ek, and then lambda 0 is the maximum eigenvector because all other real ones are negative. So why this negativity matters? Because the solution of this, which is not written probably, solution is pt is e to the power minus lambda kt ck ek. That's the solution. But when you take t goes to infinity, you want that only one, the largest eigenvector, which you reach a steady state, which doesn't depend on time anymore. That's what you want. So the steady state is unique, right? I mean, so for that, it is needed physically it is needed that all the real part of all other eigenvalues has to be negative, so that t goes to infinity, all of them disappear except one of them, which is 0, doesn't depend on time, this becomes E0. So given a matrix M, right, this matrix M, all you are looking for is the right eigenvector corresponding to 0 eigenvalue. And now how do you know that 0 eigenvalue exists? Because the determinant of x, at least one eigenvalue is 0. Whether it is exactly one eigenvalue is 0 can be proven if the matrix is irreducible. I'm not doing that, not needed here. Okay? So now another thing has to be done. This equation, if p is normalized to start with at t equal to 0, then the equation also evolve to each step, the normalization should be maintained. Like in quantum mechanics, psi 0 is 1 equal to psi t, right? So similarly here, this has to be, the norm should be conserved. So let us see that how you conserve the norm. So you have an equation, so p of t equal to e to the power minus, okay, t times m times p0. That is your state. Now, what you can see is that if with m, if you multiply b, I define a vector b which is 1, 1, 1, 1, 1. Tm. Sorry. P0. So if you define a vector b which is 1, 1, 1, then norm probability conservation is just b times p. T equal to b times p0. That's what you want, right? Because this is 1, 1, 1, this is a vector, so it is sum of all probabilities. Is it clear? Pt is just p1, p2, p3, p4, this is 1, 1, 1, 1, 1, this time that plus this time that, this is sum of, this is the norm, probability conservation. So v, which is 1, 1, 1, like this, a vector from left, multiplied by p, t has to be v times p0. So here you multiply by v from the left, you multiply from v from the left, right? But v, if you multiply on this matrix, let us say this is 1 I written, we'll check this, the column sum is 0. I think I have written it wrong. This one is q, right? Both q, okay. This one also q. Yeah, these are all q, okay? So the column sum is 0. So if you multiply with this matrix 1, 1, 1, 1, minus 2q, q, q, 0, okay? So m operating on v equal to 0, okay? So all you are looking for is the right eigenvector of m. The left eigenvector is just 1, 1, 1 for all matrices because the column sum is 0. So left eigenvector you don't have to bother. So now, just because it is a left eigenvector, v operates on m to give 0, because this is eigenvector. So this will become 0, and e to the power t0, this is 1, so that is true. Okay? So the norm of this equation is conserved at any point of time. Okay. Third thing which I wanted to do is this problem. For two-side Ising model, you wanted to write the master equation. Okay? So, yeah, I could see that some people corrected me, which means that you know how to do this. Okay? So basically, let us try this. So plus plus is a happy state because both of them are up. Plus minus is not. Minus minus is a happy state, right? I mean, so energy of this is 1, minus 1, this is minus 1, and this is plus 1, this is plus 1 energy. And you say that the Monte Carlo rate is always 1 if you are going to low energy configuration. So let us look at this, plus plus. So plus plus is minus 1, but plus plus from which configuration it can come from? It can come from plus minus, because if you flip this, it can come here. So the rate from here to here, if you go, this is minus 1, so the rate is 1. And it can also come from here, because you can flip this, and it will put it 1 here. And minus minus, you cannot go to this. This is the configuration. So plus plus can go to minus minus, like this. All the rates are given. Like you can see that plus plus to plus minus, because if you are losing, you are high, this is a higher energy, it is Q. This way it is 1. this way your lower, higher energy Q, this way it is 1, same way I have written it. Okay? Are you getting it? Okay. So now for plus minus. So plus minus can come from plus plus with rate Q, because plus plus is a happy state, plus minus is 1. So it go here, higher energy, so Q. And the diagonal you forget it at the end. Or maybe you can also look at it. For plus can lose by becoming plus minus or can become minus plus, but each plus plus can become plus minus or plus plus can become minus plus. Both of them are rate Q, so this is minus 2Q. Clear? But once you write them, all of them together, you know that the column sum comes out to be 0. So you write dp by dt equal to, I write this, and times p. This I am calling it a vector p. So this I am calling it p. And this is your matrix M. Okay? So if what is the task of the whole class, next 2 classes, today's class, the class is just find a steady state. That is all I will do in these 5 classes. So dp by dt equal to 0 means this matrix into some vector is 0. You have to find out what is that. So you multiply this matrix x1, x2, x3, x4 equal to 0 and find out x1, x2, x3, x4. Normalize it. That's all I want to do in the 4 classes. That's little odd, right? But there is the problem is that this matrix, this is only 2 sides, it's 4 by 4. If it is L sides, like 100 sides, right? I mean, it is 2 to the power L by 2 to the power L. So you cannot even write it, not even computers, right? I mean, so now question that how to do this. 10 sides, already 1000 by 1000 matrix, right? I mean, no, so 10, so that is the task, like, how to solve such a problem. This is just some matrix times B equal to 0. How to solve such problems, that's all we do. Okay. So what I do now, there is another one. So let us take 3 sides, just to understand it better. Let us take 3 sides. And all I want to do is that, let us say that if there are only 3 sides, and I take a configuration, this is my configuration C, let us say plus minus plus, plus minus plus, this one. This is the configuration I am talking about. And I am using a single spin flip dynamics, like here. What are the configuration from which this particular configuration can be achieved? Firstly, this one plus minus minus, but this could have been minus minus plus earlier, because this one just flips, first one flips. Or it can be plus plus plus, because if you flip this, it comes here. Or it can be plus minus minus, because if you flip this, it becomes this, right? So these are the 3 configurations from which you can reach here. Is it clear? So similarly, from here, where do you go? If you flip this, it becomes minus minus plus. If you flip this, plus 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 plus, and if you flip this, plus minus minus. So this is the same configuration it has come from, and it will go here, right? So if you want to write this, then you have 3 places from where it is come from. So for, let us say, plus minus plus, every column, so it will come from 3 different configurations. I have written only one here. I'll tell you what. So why I written it here, let me say that what this matrix which I'm talking about. Let us say that I'm concentrated only on the rates by flipping the middle one. Right? I mean, I'm bothered only about this one by flipping only this, one side, single side. I don't bother about the previous ones. So the configuration from which can come from is this, only this one. This one I erase. This is the only configuration it can come from. And this one can go to this configuration, right? If it is a single spin flip, right? In the middle spin, this flips. And the corresponding rate will be, okay, I will write it also there. So can you write this for plus plus plus? What is that? I am writing for the configuration plus minus plus, plus minus plus. From where does it come from? From a single flip, single spin flip? From here. What should be the rate? 1 or non-1? It's a lower energy or higher energy? Higher energy means some rate, not 1, right? I call it P. We'll see what P is. Now, so basically with rate P, it can come from plus minus. I don't bother about where it goes. At the end, you just put the sum of the thing and put it in the diagonal, okay? So the best way to write such a matrix is only to look for from where this particular thing can come from. So this one can come from plus, plus, plus. By flipping this, you can come here. There is nothing else you can do. By seeing middle thing, you can flip and come here. This is the only one. So you call it P, okay? Only from the middle one. So why I am talking of middle one? Because whatever you are doing, whatever this matrix is doing one side, next side the same thing happens, right? The same matrix can operate in the same side. So this is the matrix which operates only on the one single spin. Okay, so in other words, so if you have a configuration, something, you have a S somewhere, Si, and there is a configuration like this, right? And you want to go to a configuration, Si goes to minus Si. So what is the change of rate? What is the rate? So to know that, you need to know what is here. Let us call it, it is Si X and this is Y. The values of this you should know, otherwise you cannot say what is the energy, right? So what will happen is that if Si equal to plus become minus, so basically what will happen, that plus can become minus, that is your configuration, and plus can become minus or the reverse rate. But the rate, if you want to fill up the rates will depend on what is here. And what are the possible things can here? How many possible things, rates you can write? Huh? 4. Okay. So I'll write 4 times plus, minus, plus, minus, plus, minus. I write plus, 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 minus, minus, plus, and minus, minus. And then there are rates. And only thing is that from plus, 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 this is the lowest energy configuration. If you decrease, this has to be P. And that's what I have written. Plus, 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 going to plus, minus, plus is P. And what is the energy of this? Because you don't need to know what is here, right? Change of energy only from this to that. So this energy is minus 2. This and that is minus 1. This and that is minus 1, minus 2. This and that is plus 1. This is plus 2. So plus 2, minus 2. That's the change in energy, 4. So P equal to e to the power minus 4 beta, okay, for the Hamiltonian. So P equal to e to the power minus 4 beta. That's the Hamiltonian, that's the rate. Similarly, from minus thing, when you come here, that is also P. So minus plus minus, minus plus minus, from this, by flipping this with rate P, it comes here. That's what written here. Okay, and then, so these are the rates which I want. For the time being, I don't know, I have to erase something, so I'll erase the other side. So this is the rate which I'm talking about. I'm only talking about this side. Once I take care of what happens this side, I can use the same here, same here, same here. So if you have a L sides, every configuration can arrive from L such configurations, and it can go to L configurations also by just flipping, flip, come here, first flip, second flip, third one flip, fourth one flip, like that. L things can be flipped. Now, to describe this, we will use, like in the previous class, you know, in quantum mechanics, you use a vector product state. When you have to, you know, you have a Hilbert space, and there is a, so if you have two systems, it's a direct product of these two Hilbert spaces, right? So we will describe our configurations like that, but it's not a vector product state. We will write a matrix product state. Let us see what it means. Okay. So the definition, so matrix product answers. That's what we start. So what we do is that we write in steady state, that's a statement, that's the answers. We don't know whether it will work. We'll start and then we see what happens. Okay? In steady state, weight of a configuration. Why I'm calling it weight? Why not probability? Because once I find the weights, I can normalize it later. So I'm calling it weight of configuration of a configuration, and configuration in Ising model, let me call it SI. Okay, is given by equal to trace of product over I x, which is matrix of SI. Okay, so what does it mean? That you have a configuration S1, S2, S3, S4 up to SL, and these are something which is there. What I do is that for S1 I write a matrix X of S1, for S2 I write X of S2, here X of S3, like that, X of SL. So how many matrices are all together? How many different type of matrices I'm writing? L. What is the value of S1? Plus or minus. So for each one, either it is X plus or it is X minus. So there are only two matrices I'm talking about, right? Not L. Okay. So basically what happens is that if you have a state like plus, 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 minus, plus, minus, 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 and probability of this, I can say that X of plus, I'm putting a different notation, equal to D, X of minus equal to E. This is the notation I use. So what I do, probability of this, I will first trace, and plus I will put D, plus D, plus D, this E, D, E, E, E. For any configuration, for any problem, you can always write this. I mean, you are not doing anything, just rewriting it in a different one. I mean, you have to say that are there matrices which exist, right? For Ising model, we want to figure out two matrices. No, if you have a Q-state force model, 0, 1, 2, then you have three matrices. Yes. Yeah, so for disorder, right, I mean, that is some way, it will appear in the rate somewhere, right? No, these equations will be different, right? It is not that you have, so for the disorder, if a system, Ising model with disorder, do you have different number of configuration than what you have earlier? No, right? It's only the M will change. If you have a disorder, the matrix is some way disorder, and you have to write. Yeah, we'll see. We can try one disorder problem. I don't have that, but we can try. What? Weight, basically, I'm just saying that weight with the probability. So probability, I can call it weight, yeah. Because probability means that, the normalization factor is also there associated. So probability means sum over all configurations has to be 1. I'm not bothering about that. Sum can be anything, but a number. I divide it later. That's the reason I call it a weight. So weight of a configuration is just this. That's what I'm assuming. Okay? So then, what will happen? Like, so for example, if 3 sides, this one, like, how to say, the probability is a 8 vector, right? The probability, I mean, like 2 sides, I have written P plus plus, P plus minus, P minus minus, P minus minus, and then there is a matrix which is 4 by 4. Similarly, 3 sides, you have 8 by 8 matrix, and the vector is 8 dimensional. So this one will replace by trace of D. This will be trace of D, D, E, like that. I don't know. We want to figure out what is D and E at the end.
S can take 2 values, plus 1 or
Minus 1, yes. In Ising model, that is correct.
So what does it mean by corresponding real matrix?
I don't know. I'm just say that at the beginning, this is answers. Can I write it? If you can write it, we can see some advantages.
I'm just trying to think that.
Physically.
Yeah, no, not physically. Just mathematically also, I have some value of S, 6 plus 1. Now
Yes.
I'm asking some matrix will be corresponding to plus 1.
Yes, but that is a trace, right? The weight is a number, trace is a number.
Yeah, so but what is that matrix that we are looking for?
I don't know, we'll figure out.
So means what's the motivation behind it?
If you can find a solution, will you be happy? Right? For Ising model, for example, we know it is e to the power minus beta e of this. All I'm trying to do is that I forgot for the time being that I don't know Ising model. I know only this dynamics. This is the dynamics. Some spins follow this dynamics. How do I know that it is actually leading to Ising model? I don't know at this stage. I'm trying to figure out that given a dynamics, can I figure out D and E? Right? And for Ising model, I know it a priori. Right? I mean, because I'm giving you, I'm trying I'm putting that effort to figure out that the matrix DE, once I figure out logically, we'll find out that this will correspond to the Ising steady state, given this is the dynamics.
What you pretend here, the 8 cross 8 matrix,
Yes.
is it an example of one of the D or E?
Is it an example of?
Like, is it one of the examples which you are referring to the X? I didn't see the. So you wrote a matrix for one spin, right?
Hmm.
For a single side,
Yes.
you written a matrix. How do you show me?
Yeah, Lord, just wait. So far, I don't write anything. This, whatever I've written is clear so far. I mean, it may not work. You may have all you are trying is that it's a apprehension that, oh, maybe, what nonsense, everything you are putting D in, every problem you can write D, what nonsense, this may not work. But I'm telling you that it will work and I will show you that it will work. Wait. Okay? So what we do now is that what is your probability? So your probability vector at any point, the steady state probability, that's a state, I'm only talking of a steady state probability or steady state weight, right? So that's a vector. So I should write this equal to P plus P plus minus, like that. I should have written like that, but I will not write like this. I will just say that this is because for each configuration, for 3 sides I'm saying, for each configuration, the weight of plus is what? DDD, trace of DDD. So I will write trace of DDD, DDE, DED. So trace of a vector, by notation I am using trace of this. I just don't want to write this. Okay? So this is my notation. So this is trace of this. Each of them is a number, right? Right? I still don't know what is D and E. All I'm writing is the probability vector has to be written like that. Okay? So this first thing you will see very quickly that is just DE cross DE cross DE and trace. Convince yourself that this is same thing as this. So P vector equal to this. Let us try this. Not yet. D by is I am using as a vector. So let us say that what is the direct product means. Kronecker product or direct product means. So AB, like there is something AB cross CD, but the definition is just, so this equal to, you write it one of them, which let us say CD, and each of them is AB. Okay? AB, that's the definition. So what it means is that D cross C, let us write what is D cross C cross D cross C. D, you know the direct product, right? You know how the direct product matrices work, right? So if you have A, B, C, D into P, direct product with P, Q, R, S, and P, Q, R, S is, let us call a matrix M. This matrix is called M. Then what will happen is that the resultant is AM, BM, CM, DM. That is the way it works, right? So I will also use this. So DE, D cross C, DE cross DE equal to DD D, so this will be D, DE, and each of them is again DE times DE. It's a simple product. So that is DD, DE, ED, EE. DD, DE, ED, EE, and then I have a trace outside. So I will get P plus plus, P plus minus, P minus minus, P minus plus, right? So this is, P vector is like that. Okay.
But for it to work like that, there should be a specific order of pluses and minuses in the vector column.
Two plus number of?
For it to work like that, there should be a specific order of pluses and minuses in the vector. So we.
Yeah. The order has to be taken. Yeah. One of whichever the order you take, one of the order will work. You define one way. Define the way you define direct product. But do you get anything? So if it is a L, if the product of L, then you get all the states 2 to the power L vector, right? Because each of them is 2 L times 2 to the power L vector you get. Trace of each of them, right? Agreeing? Okay. So your P vector, let us write it, P vector equal to DE cross DE cross DE. No, I'll write more cross DE and like that. Now let us say somebody.
Trace of there.
Trace is there. I mean, of course trace is there. Otherwise it cannot be a matrix. Trace is there. Trace is there. Okay. So this is my probability vector. So now for a general configuration, how does this M we want to write some way? What is your matrix? This M, dp by dt equal to mp. So what we have, these are L sites. Okay. So L sites is, let us say, talk of a configurations like S1, S2, S3, S4, S5, like that. So what will happen is that if you take this as a matrix M and operate on first 3, then it will flip only S2, right? Whatever happens by flipping S2 is what M is doing. Huh? Is it clear? So with a single spin flip, this matrix tells you that if the middle spin flips, what is the matrix M which takes care of the middle spin flip? This thing is middle, right? Because all what happens is that plus, so talk of this, plus 1, right? So why does it from where it can come from by flipping in the middle spin? That's what I have written it here, right? Let us say plus. By middle spin flip, this spin you want to flip, from where it can come? From here. Because this one, by flipping, it can come here and with a rate 1. So all spin flips are taken care by this matrix. Are you agree? So if you have 3 spins, if I operate on S1 by rotating this matrix plus operating S2, same matrix, I can do this. But if you have L spins, I have to operate this one, keeping this intact, and then operate on these 3, keeping other things intact, and then keeping it these 3 like that. I have to find a matrix which will operate on these 3 only, keeping the other things constant.
So you in beginning you told that we are just looking at the flipping of middle spin, not at the side spin.
One spin. This is any one spin can be middle.
Yeah. So why we are writing in our matrix just middle one by one?
And let me write a equation, and then after that you ask. If you are not convinced, we will do it again and again and again until we are convinced. So let us write it. So I am writing it. So let me define matrices. This particular matrix, I am calling it a K, which is an 8 by 8 matrix. Okay. Now I am defining matrices MK. I first define M1, then you know what is MK. M1. M1 equal to K direct product with I. These are I2. I mean these are 2 by 2 matrices. And total there are L minus 3 I's. So if this matrix operates on a state this, then it will change only these two, do nothing to the rest of them. It's like quantum mechanics, it's the same thing. And now I'm just saying that the total matrix M, so Mk equal to I cross I, and this K is 8 by 8, and total, this dimension of M1 is 2 to the power L by 2 to the power L. Agree? So all Mk matrices are 2 to the power L by 2 to the power L. These are I cross I cross I. At kth place, you have a, sorry, at ith place, Mk I have written, Ml. At lth place, you have a K, and then all others I. So all the matrices are 2 to the power L by 2 to the power L dimension. And I just say that M, total M, equal to simple sum over I, Mi. So now you can ask questions, and if you are not convinced, we will do it again. So what happens is that this M matrix contains all the spin flip here, spin flip here, spin flip here, spin flip here, like that. And somewhere, whenever, so M, what does the M do? Mk, so Mk, first thing is that Mk takes care of Sk, Sk minus 1, Sk plus 1 with clipping taking place, at kth site. Right? That is the, so now every configuration, because it is a single spin flip, the configurations here, flip here, here, and that is, you get all the flips. All the configurations you can come from and go to. So this M is a 2 to the power L matrix. This is sum over Mi. It's a, no, this is the K matrix, 8 by 8. No, this is 8 and these are L minus 3. 2 times 2 times 2 times 2 to the power 2 to the power L minus 3 plus 8 is 2 to the power L. 2 to the power L minus 3 into 8, 8 is 2 to the power 3. Okay, so 2 to the power L total. And this 2 to 8 matrix is this. This is nothing different from quantum mechanics. Quantum mechanics, what you do is that you have a vector states, right? I'm symbolically using this dE as if they're states. Like, so you have a states, and then when you say that, I think you have already discussed this, like, when you have a state like 1, 1, 0, like that, 1, 1, 1, and you want to operate A dagger in 1, 1, 1, let us say you want to operate. So this is actually means that A dagger cross I. So which means, right, plus you can have a I cross A dagger, which means that it will, first one it will operate this, keeping this intact, then it will operate on these two, keeping this intact, and then you sum up. That's all I'm doing. And this, the way, so this is like a Hamiltonian decomposed into site variables. And this is the interaction, which is all interaction, all dynamics is kept here.
So the resultant matrix M is
like, sorry, just one second. Like in quantum Hamiltonian, you can write H equal to summation over I, some HI, and HI can be AI dagger AI plus 1. HI is operator, can be AI dagger AI plus 1. But this means that AI, ith place, I dagger I plus 1, all other places I, and you have a state vector on which you have to operate. That's the way the quantum mechanics works. So is it clear? Yes?
The way you have written MK,
Huh.
it flips the K plus 1 spin, right? Like M1 flips the second spin.
No, I mean, yeah, okay, so whatever, right, so middle spin at a kth spin, that's my definition. So M1 spins, M1 spins second spin, K plus 1 spin, yes. K plus 1 spin. In together they flip everything, because M1, I mean, thank you. So M1, because M1 in the first, it takes care of first three and flips the middle. So it's a second spin. M1 talks of second spin. I should have called this M2 if I wanted it K1. But I mean, let us keep it like that. But under the sum, it's the same thing.
So is it true that the resulting matrix M is like block diagonal with blocks of K? Like K, 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 K?
No. That is sum. I don't know what is A plus B cross C plus D. A cross B plus A cross B plus C plus D, C cross D. How can you write it in terms of some other factors? And that is the whole thing called entanglement. I mean, you just cannot write it like that. Because the plus is not a point. But you can multiply. Multiplication is fine. A cross B, I'm writing it this way. Dot C cross D equal to AC cross BD. That works. Not adding. Adding is a difficult task in terms of Kronecker product. That's the point. Okay. Is it clear now? So given this, let us pretend cheating a little bit of do. And so for this is we are talking of Ising model, and this whatever we have written is for Ising model. And we know that there is a detailed balance. Okay? We want to figure out what are the matrices DE which satisfy this. So let us try that, assuming this is your steady state, I mean given by DE, apply steady state condition. Okay? What is the steady state condition? Basically means that P operating on this is M1 operating on this plus M2 operating on this. So M times P equal to M1 times P plus M2 times P plus M3 times P, like that. And you want this to be 0, right? But what I want, let us say that M1 times P is itself 0. I mean, of course, this is not needed. This is not needed. But if I am demanding that condition, then automatically it will be satisfied, right? MIP equal to 0. Then this equation will be satisfied. It's not a requirement. And M1P equal to 0, we want to say that that is actually the detailed balance condition for every configurations. Let us look at this. So when you say M1P equal to 0, so any MP equal to 0, right? I mean, doesn't matter where they are, because this, so which means that this matrix operating on DDD, that has to be 0. That's all you are like. So this one into this equal to 0. So let us take the first one. So what is the first one operating on? I think of, there is a here, and this is plus DDD, DDE, like that. This column is there. So the column here is DDD. I don't know. Imagine that there is a vector, I don't know what to write. DDD, DDE, DED, DEE, like that. So all the 8 elements are there. Now multiply this matrix into that element, which means that minus P times DDD equal to 1 times this and nothing else. Everywhere else is 0, right? So minus P times P, this, and this times that, and trace has to be 0. So the first equation you get, M times P equal to 0, is that P times minus P times DDD, trace of DDD. Acha, by the way, the other things you do not know, because you do not know where you are appearing. Some M somewhere, MK, right? Operating on P, you are calling it 0. So this P, wherever you are appearing, this is plus, 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 but other things are, you don't know. So other things are X, Y, Z, something, whatever the value, it can be plus, 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 minus, whatever, I don't care. And kth place, it is plus, 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 and this plus is the one which you are, this is the place where this is operating. Plus, 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 times P, trace of that. Are you getting this? Is it clear? No. Okay. This I need, this I don't. Acha, when kth matrix operates, right? Which are the set of, so in the position, there is this 2 to the power, this vector is 2 to the power L, right? So what are the matrix element, each of them? Each of them is trace of x, y, z, like, I don't know, S1, actually let us call it S1, S2, S3. So if you want mk, then kth plus, this is sk, sk minus 1, s of k plus 1, and then there are other things. So when you have mk, any mk operating on this matrix, then this will operate only in these 3 places. These 3 places. So these are all x's, x this, and these 3 places I am specifying because these 3 things are specified by this matrix. This matrix will operate on these 3, and rest of them are unchanged. Right? Are you getting the point? Where does mk operate? K, k minus 1, and k plus 1. So these 3 things can be plus, 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 minus, 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 plus, like that, and I am operating that. So everywhere else this is remain unchanged, and this is unchanged. This matrix operating on this will give you some vector, some other vector. I am writing each of them. First one, what is the first equation it will give? First equation it will give minus p times ddd plus times ded, that equal to 0. Okay, so basically p, so first one I am taking it plus, 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 so this will be plus, plus, plus. Other things I don't care. This is p minus p times that plus ded, because this one multiply here ded. So plus 1 times ded, no, s1, s2, like that, ded. This is ddd. Okay, this, and after that, this is also trace. This equal to 0. That's the first equation you get. Is it clear? So then what will happen is that inside the trace, so this will be trace of all S1, whatever, the first element, first condition from here you get, minus P ddd plus ded equal to 0.
Shouldn't there be identities under the trace instead of
Yeah. This is this identity that remain unchanged. Whatever the matrix that remain unchanged, here it is changing, because after operation it will change, and that is the steady state, right? In the steady state probability. So let us say that why it is a steady state. So because trace of this is the probability of this, and if this equal to 0, which means that this p times e to the power ddd has to be this. That is what the detail balance is, right? Because this one you have written only from the detail balance. Is it clear? So what is the condition? So this condition reduces, because this for anything, this can be anything, and dot dot dot, this has to be 0. This can be anything. So it is necessary that this has to be 0. Right? It is important that this has to be 0. So which means that first equation you get minus p times dq, p minus p dq plus ded equal to 0. Right? That is exactly the steady state condition. Okay? What is the second equation? If you understand this, can you tell me the second equation? From this one I multiplied. Now this one. Minus dde plus ded dee equal to 0. Okay? And write the other ones also, complete them. I think I should write it here. Erase them and write it here. This I don't need anymore, because it's going there is difficult. So P times dq equal to dEd. From here you get d square E equal to dE square. From here you get dEd. From here equal to P dq equal to dEd. Okay. P dq equal to dEd. From this one, d square E equal to dE square. Okay, and next one, this one is, I think I just replace d by E, whatever happens, happens, because there is a symmetry. So I will just write this equation with d replacing E replacing by d. Those are the one which is written there, has to be. So this has to be P EQ equal to E d E, and then d square E square d equal to E d square, P EQ equal to E d E, and then E square d equal to E d square. But then you can figure out, then you can see that same equation appear twice. Why? That is because, when there is a rate, when you are talking of this rate, to get the detail balance, this way you can, so you can write once for this and once for that, but the equation is the same. Right? In the master equation, right? Each term appear twice. So the equation is the same, it appears twice. You have to solve these eight equations you have to write. For 3-side problems, if the dynamics is a 3-side dynamics, you have you have 8 conditions on matrices. Now question is that, can you solve them? And one thing we have put here is that as if each M1 acting on that has to be 0. But that is not necessary. That is something which is using because we know it is equilibrium situation. So in general it will be different, and we will see what different it is. So now let me try to get a solutions and give you some surprise here, hopefully. So let us say that what kind of matrices will satisfy this. So let us write the equation in compact. I will erase this. And d square, this is also same, and E square d equal to this. It's 4 equations. Okay, so I have P E cube. So you have P times E cube equal to E d E, and E square d equal to E d square. Okay, so now you look at this, we don't know what is Ising model, we just kind of, the rates are given and we are writing this matrix from the rates and try to find out conditions DE should satisfy, and you can figure out matrices, then that is the steady state solution.
Every I will get but every MI what else?
Yes, so because you look at what is MK, it's the same equation, right? It's the same equation. And that is the reduction which you did. Because 2 to the power L matrices you don't want to handle because you have only 8 conditions. If it's a 3-side problem, we have 8 conditions to bother about. Okay? So now let us say that how to solve it. Right? Are there matrices which satisfy these equations? Okay, so here I don't want you that instantly you tell me that, okay, there are matrices which is giving me the solution. It requires little effort and I don't know how exactly to proceed. Try to figure out the matrices. So for this one I can actually do it logically step by step, but most problems you will not be able to do it, like you have to try and fail and try and fail, sometimes months. But if you get it, it's fantastic. Okay, so let us say that first thing you demand is that, let us say that D is invertible, good matrix. So let us say that D and E are invertible. D is invertible. D has an inverse. That will be true for E. Whatever I make for D, that the same argument will go for E. This I need, I'm not erasing this. D has an inverse. If D has an inverse, then you can multiply D inverse both sides, right? Then you can see, so if D has an inverse, from this, if you multiply D inverse in both sides, this side is D inverse and D inverse, then these goes away. So PD equal to E implies 1, let us name the equation, 1, 2, 3 and 4. So the first one implies, so if D has an inverse, then P times D has to be same as E. So it means D and E commute. If D and E commute, then the problem is very trivial, right? I mean, there is nothing interesting here, right? I mean, that is not something, you want non-commuting matrices. Otherwise, this matrix product is just D to the power as many, E to the power as many. And that's a kind of, equal configuration. So if D has an inverse, then PD equal to E, so D and E commute. So that is not something which you want. So D doesn't have an inverse. Okay? So if D doesn't have inverse, basically means the determinant of D equal to 0. Or D has at least one eigenvalue 0. If D has an inverse, then D is same as E, up to a constant, multiple. This equation, P dq equal to D ed, I put D inverse here. So this one is identity, this side it is E, and dq, that is just PD. So PD equal to E. So D and E are no different, they commute. So you are looking for a non-trivial result solution for this, and this is not a solution which you want. Sometimes you have to that's the only solution which you have, but here we are looking for non-trivial solution.
Could you explain to which solution does this case correspond when D and E commute? Which solution?
Equal to T equal to P equal to 0. If D commute, there is a solution, no? When T equal to infinity, when beta equal to 0, then everything is, it's a tussle. There is a solution here. So let us say beta, P equal to 1. Wait a minute. Let us proceed. I mean, suggesting that what happens if you proceed with that solution. So if P dq, so E equal to PD. So you start with this E equal to P times D. You start with that. Now you put it here. This is dq, this is because E, so if you replace E here, you get a P here, and here you get P square. So P has to be same as P square. So it means P has to be 1. So of course there is a scalar solution when P equal to 1. And when P equal to 1, this rate, P equal to 1 means T equal to infinity, P equal to 1, this is plus going to minus with all of them equal rate irrespective of what is in the neighborhood. So it is just arbitrarily going flip, 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 flip. You are not looking at anything. So then all configurations are equally likely. Right? So when you have this solution, it's not that the solution is invalid. That is a solution, but that's a trivial solution, and it demands that P equal to 1, which is at T equal to infinity. We are in right track, which means we are in right track. Okay? So now what you have?
That is given that you have detailed balance. If you didn't have detailed balance, then
Yes, we'll go slow. We'll arbitrarily write it, alpha, beta, gamma, delta, whatever you write. Then you don't know detailed balance, you don't know anything, how to solve this problem. That is the question, main question. This is not matrix product, but I'm giving you that in the problem where you know the solution, it gives you the.
invertibility of these.
Mhm.
If you didn't have detailed balance, then would that be a trivial solution? You could have that.
Yeah. I mean, every problem has a trivial, right? Because there are rates. Somewhere in the extreme limits, you can have trivial solutions. It depends on the problem.
What I'm saying is that the assume in detailed balance is not there, then when you talk about this inverted solution,
It is nothing to do with whether it is detailed balance or not. Once you get an algebra, then you have to look for what are the solutions. Sometimes in some conditions you can have a trivial solution. The algebra can give you a trivial solution. Some conditions, and the conditions are physical. Here I am demanding that a condition, I mean you are saying that of course it is not that D inverse doesn't exist. Yes, D inverse can exist. If you demand that D inverse exists, then you demand that P has to be 1. You have a P which has to be 1. And P equal to 1 correspond to just symmetric exclusion process.
Sir, if we put E equal to PD in second equation, then we will get P dq equal to P square dq.
Huh.
But you said we will get D square equal to dq.
Do you get anything different from P not equal to 1?
Yeah, P equal to 1.
Fine. Okay. Then what is the, okay, yeah. Okay, so this is not a solution. This is a solution but for P equal to 1. But we don't want P equal to 1 for general P. For general P, determinant D has to be 0, right? So you want a matrix for which the determinant has to be 0, D has to be a matrix, and now you are left with nothing. You just keep trying. Okay, so one thing is that one of the eigenvalue has to be 0. That is the one you have to keep track of it. And so now what you do is that D, you write it as a outer product of two vectors, is a projector. Okay, so write it D equal to D1, D2. Something, I don't know what is D1, D2. Already I don't know one, and I'm writing two more things which I don't know. So E equal to E1, E2. These are the outer products, this is matrix. So now what will happen is that, and now we put these conditions there. First thing, we just say that so now what is D square? D square equal to D1, D2, D1, D2. Okay. What is D cube? Can I erase this? You know, trivial, you know, you remember. D cube. Now let us put it cube. Then it is again D1, D2. I think I did not do mistake, so let me write it. D square equal to D1, D2, D1, D2, right? So I just say that D2, D1 is a scalar, na? D2, D1 is a scalar, I call it delta. D2, D1 is same scalar, D2, D1 is same scalar. So that is basically mean that D to the power k equal to delta to the power k minus 1 D. In this choice gives you this generally. Is it clear? So similarly, so let me write it again. E to the power k equal to epsilon to the power k minus 1 E. Okay, so E2 U1 equal to epsilon D2 D1 equal to delta. This is what you want. So now, can you find matrices of this kind? And again, another thing has to be that it has to have one eigenvalue. So now let us call it trace of D. Okay, another thing also you say that trace of D equal to trace of E equal to trace of D. Okay. Epsilon is trace of D, right? Trace of D is the trace of D2, D1, D2. So that is a D2, D1. That's a scalar. Okay. That is one of, yeah, convince yourself. I'm not going to do that. trace of E. So this is like trace of AB equal to trace of BA. That's the same way even the vectors work. Aha, I erased it. Yeah, okay, let us erase it. I think, yeah, let us erase this. So now we just, so now you need the trace, one of the eigenvalue is 0, trace has to be 1. Can you figure out matrices, 2 by 2 matrices? Suggest. So I am taking, I mean you can take many choices. Let us try with 2D. These are the only conditions we get. So D equal to epsilon A 0 0 E equal to, sorry, delta 0 0 B and epsilon. So this is trace is delta, right, and determinant is 0, because this is, I mean once this is 0, this is reducible, right, I mean the eigenvalue is 0. So D square, one of the eigenvalue is 0 and trace is D. So what is that? What is your D1? So this is just delta A into 1 0. This equal to 0 1 into B epsilon. Okay, so this is D1, this is D2, this is E1, this is E2. Right? So this is your E1 and this one is your E2. This one is D1 and this one is D2, but D2 is 1. I mean somehow I don't know why I have taken this, but 1. Yeah, okay. Okay, 1 is just 1 0 vector, 2 is just 2 0 vector. So E2, so this is the vector. Okay. Okay, so D matrices are known. So now let us see that once the D is known, you still have choices like what you can take A, B, but then other conditions has to be satisfied. So let us take the first one, P DQ, because you want to determine also P. This one tells you this is DE and this is E square. So E square is delta times E. D square is, let us take these equations. Equation 2. What is say? D square E, but D square is delta to the power delta D. D square is delta D. So D square equal to delta D, delta DE, and D square is again E, epsilon. So delta has to be epsilon. So I cannot take the delta as epsilon, I call it delta. Right? So now you have to, and that is also satisfied by this equation, it's not a different one. Only one equation has to be satisfied, P dq equal to DED. So what is P dq?
How do you say that these traces are epsilon and delta for these traces?
Trace of outer product of two vectors equal to trace of, sorry, equal to B A, proof, homework. Okay, I don't, because otherwise it goes too long. Okay, so now P dq equal to delta P delta square. So let us write it, P dq equal to DED. Okay, so P dq is delta square PD and equal to DED. Let us write it D1, D2, E is E1, E2, and D1, D2. Can you calculate for me D2, E1? What is D2? This is what? Total, calculate full thing. So this is d1, d2, this one will be d, something into d. So you have this scalar thing, you have to calculate this into d. So something equal to something into d. And then you have to equate delta square p equal to this. So what is that? d2 e1. What is d2? This is d1, d2, 1, 0. And e1, so this is just b equal to b. E1 means this one, b times e epsilon. So this is the first element of this, so this is 1, b. So this one is b, and e2 d1. E2 is this second element of d1 is a. So this is ab. Is clear? You know matrices, if nothing multiply, d, e, d. Okay? Epsilon equal to delta. Yeah, because epsilon we have from this equation, epsilon becomes delta. So I am putting epsilon equal to delta. And AB still has a choice. I can put them 1 because I don't arbitrarily I am putting them. Simplest choice is 1. You can put anything, it will not, I will tell you why anything would work, we will see later. But let us for the time being put this equal to 1. So delta equal to 1 by, you can also put P, I don't care. So this is A, B equal to 1. So I am just saying that A equal to 1 equal to B is still a choice. It was not needed, but any matrix which works will work. Right, I mean I can take this. And in a metric, okay, we'll see why there is a choice, we still left with a choice because of that. So delta equal to what? From here, if AB equal to 1, delta equal to 1 by P, because D is there, so delta equal to 1 by P. Is okay? So delta equal to 1 by square root of P. So now, after all this effort, what we get is that D equal to 1 by square root of P, 0, 1, 0, and E equal to 0, 0, 0, sorry, 1, 1 by square root of P. So now, what is the, if you, once you know DE, then you know the steady state. We can calculate the partition function directly. Given this, let us calculate the partition function. Then we see that partition function is t to the power L, and we will see that in this is the Ising model case, so we can see this. So your partition function Z equal to, I am just demanding that, trace of D plus E whole to the power L. Are you agreeing? What is the partition function? Partition function of sum of weights, right? Partition function by definition equal to summation of all configurations with whatever weight of that configurations. I'm calling it weight, not probability, because anyway the sum is not 1. Whatever the sum, that's a partition function, right? So now all configuration means what? D, 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 E, like that, na? Right? All configuration means trace of, in matrix product, this is trace of D, 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 trace of plus trace of D, 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 E, but this is what it will be generated by this, because if you write it D plus E, D plus E, D plus E, like that, then D, 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 so there are 2 to the power L elements, and each one corresponds to the probability. So it's very simple, the trace is D plus E to the power L. So then, if you know that Ising model trace is T to the power L, your T matrix has to be 1 by square root of P, 1 by square root of P, 1, 1. But a matrix, you know, at the partition, so let us look at what is your P, which I erased. So P is e to the power minus 4 beta j. P is e to the power minus 4 beta j. So 1 by square root of P is e to the power 2 beta j. E to the power 2 beta, e to the power minus 2, no, e to the power 2 beta, 1, 1, e to the power 2 beta. Right? I mean, this is what you get. But this can be also written as is e to the power beta whole into e to the power beta, e to the power minus beta, e to the power minus beta, e to the power beta. There is a constant and it doesn't matter because L is fixed. Any multiplicative factor doesn't matter in the partition function. So this one is there or not there, it doesn't matter. And that is the reason you could not fix it here uniquely. One constant you will still have for normalization because you cannot fix. Here you have two constants because you, AB has to be 1. Okay? And anyway, AB has to be 1, it's not that. So basically you get the partition function of Ising model. Okay? So what I do is that initially when I write these rates, I did not get that there is a Hamiltonian. I did not write that T, it is e to the power minus beta h or something. So given a dynamics, I'm generally trying to figure out whether what is the steady state of the problem. And the steady state which I get in Ising model is exactly what I know or what Boltzmann had said earlier. Okay, that is we get it. But then the method is very general now because it's nothing to do with what I write. So I can say that I have like these equations which I wrote like plus, let me write it, plus minus plus like that. Okay, no, we'll finish it. Many people are looking at the words. We'll finish it. Don't worry. Yeah. So this one, because so I can call it plus goes to minus. This is S and S prime. Let me write it explicitly. So let me write a general rate. So I want still a single spin flip. So let us say plus S plus S prime going to S minus S prime, and it can come back. Forward rate is P S S prime or alpha S S prime, and backward rate is beta S S prime. So you can have 8 variables, right? I mean, this is a model. You know the dynamics, but do you know the steady state? This will not necessarily, one of the example here, when alpha plus plus equal to alpha minus minus equal to P, all other ones. One example, this particular choice is Ising model. We have proven. But you can write any dynamics, right? So the method is very general, and you can write at least the matrix, the algebra, what I wrote it here, like these 4 equations which I write, this is called a matrix algebra. So question is that for any given dynamics, you should be able to write the matrix algebra. Okay? So what we have not done, okay, wait for a second, and then we'll, I will take my 5 minutes. Don't, so, so what, if you have questions you can ask now, or just one more thing which you want to say. What are the things which you have not done yet is that you have been asking, Sir has been asking also. So the question is that we put each individual one as 0. All you wanted is that M1 operating on P, M2 operating on P, M3 operating on P, M4 operating on P, the sum has to be 0. It was not needed that each individual one has to be 0. Okay? So how to write the matrices such that the sum is 0 even though the individual it is not 0. Okay? That is, we say that a cancellation scheme. We'll use a cancellation scheme, we'll write a general cancellation scheme, then the matrix product answers will be complete. Okay? So then what we have is that given any dynamics, I don't need to know whether it's a Hamiltonian or not Hamiltonian. It's a non-equilibrium problem where maybe there is no Hamiltonian at all. You cannot write a Hamiltonian form, but you can still have a steady state. Okay? So we'll try to figure out that. So for different dynamics, we'll try to write matrices, and what are the, this is called a matrix algebra. Given this as a matrix algebra, what are the solutions? So what are the solutions? Just because it is trial, unless, I mean, I could not have done it here instantly unless I had done it earlier. Okay, so it is right, you have to try. That is here, I don't know the procedures, but you can write the algebra here. Writing the algebra should be easy. And all I do in my tutorial, is that one of you, like at least some of them, write a dynamics, other one write the algebra. Right? Write any dynamics, you should be able to write algebra. Whether they have a solution or not, a different one, but everyone, I mean, at least this is a big hope, that this much you should be able to know. And in next classes, I will try to solve in some specific cases which is interesting. Okay? So as far as the matrix product answers, the idea is clear. Only one thing which is still not there, because I'm still doing it, is in equilibrium. In non-equilibrium, you have to make the sum. It is not individually everything is 0. It's not a detailed balance condition. You don't know whether detailed balance is satisfied. So you cannot use M1 equal to 0, not like that. So the sum has to be 0, and we will see how the sum goes to 0. Okay, I stop here, and questions.
Is there a reason why one of the eigenvalues is 0 for D? I mean, we found that D determinant is 0 for D, right?
Yes.
Is there a deeper reason, is there a physical reason as to why D has to have determinant 0? I mean, I can understand from the equations, D non-zero will give us trivial solution.
If you know that it is partition function z equal to trace of t to the power L, right? So this is basically as if at each point you have written a t, right? And then you have a trace. So you could have, without knowing anything, you could have guessed that t11 and t22 are the matrices, because t11 plus t22 is t. If this is D and this is E, then this plus that is t times 11 plus 22 equal to t times identity equal to t. So the matrices are just D and E, and this one has a 0 eigenvalue.
So this algebra can be also used for fermionic systems when we can say that
This is kind of a classical form of fermionic system, because hardcore interaction basically means that at each site you have only one particle. You ask the other question, can it be used for bosonic systems? Yes, we will do it in the last class if we have some time.
Can you once define X subscript
So if you have a configuration which is S1, S2, S3, this is a configuration. But the configuration is not general one. S1 equal to plus, you tell me what is S2, tell me. Minus. Who was asking? Minus. Let us say minus, and this is plus. Okay, so if this is the three sides, then for this I write x of S1. S1 is plus, I write plus. This is x of S2, x minus, x of S3, which is plus. So for a given configuration, this is x plus, x minus. You cannot get anything different than x plus and x minus. I don't want to carry this index. I'm calling it x plus is D, x minus is E. Yes?
For interaction increases, then the equations also increase.
Interaction range.
Yes, because since it is Ising, I think you have can similarly with
Let us, answer is yes, but I don't want to say it that way. No, I'm just saying that this is not interaction. So there are the dynamics is two-side, right? It's a three-side dynamics. I don't know about the interaction. For three-side dynamics, it is this. The three-side dynamics doesn't necessarily say that it's a short range or long range or whatever. I can give you example of a two-side dynamics where the interaction is long-ranged after the class. It is not to do with, so it's the three-side dynamics, that's where I fix it, not the interaction range.
same thing can be done with 4x4 matrices, right? Or two sides.
This is the minimal representation we look for, right? So any matrix, let us say D is a 2 by 2. If you want another representation, yeah, I will ask you to find another one. But then this D, if I say that D, 0, 0, This will also satisfy the same equation trivially. So the dimension doesn't matter, and there is no uniqueness here. This will trivially work, na? dd equal to, just dimension is 4 by 4, and just put, if d works, then d cross I also works. D cross I also works, yeah.
So I was asking about the M matrices that we are forming,
Yes,
the K matrices, so to speak. So we have this 8 by 8, right?
yes,
Because we are considering three sides.
yes.
So if we, instead of considering 3, we consider 2 sides, and then we can put over.
No, in the Ising model, the dynamics is 3 sides. Because if you flip a spin, because it is interacting with its neighbors, to know what is the energy change, you have to know what are the neighbors. Okay, so let us try writing a dynamics this. It's a 2-side dynamics. But will it give a Hamiltonian? I don't know. Will it give you anything? I don't know. I will ask probably a teacher. I think let us, the recording please, hello? Recording stop kar do. Ha. Kind of, the class is over, so you can go for coffee. If you have questions, you can ask. Yeah. Yeah, where